this worksheet does a couple things. It is a chance to practice with finding the best response, finding Nash equilibria, finding dominant strategies, and identifying them. But it's really about the prisoner's dilemma because I define the prisoner's dilemma. Both players have a dominant strategy, and the dominant strategies lead to a worse payoff for both than the other strategies. But when I asked about it on exams, I would show a game and say, is this a prisoner's dilemma? Students seem to want to make up their own reasons why it was or wasn't, and it's really just about those two things. If both things are there, it's a prisoner's dilemma. If they're not both there, it's not. And those are the reasons why it's a prisoner's dilemma, because it fits the definition, not because it has anything else. So, this is just to remind ourselves, so both players have a dominant strategy. And the dominant strategies lead to lower payoffs for both. Than the other strategies. Okay, so now let's check. We want to find the best response. So if player 2 chooses left, player 1 chooses up because 20 is bigger than 10. If player 2 chooses right, then player 2 chooses up because 10 is bigger than 5. So we have a dominant strategy here. Just make a note of that. And then for player 2, if player 1 chooses up, 20 is bigger than 10, so player 2 chooses left. And if player 1 chooses down, and we're in the bottom row, 10 is bigger than 5, so player 2 chooses left. So we also have a dominant strategy here. So, both players have a dominant strategy? Yes, we've got that. Do the dominant strategies lead to lower payoffs for both? No. Actually, the payoffs here, when they both play their dominant strategies, are the highest on the board. So this is not a prisoner's dilemma. Because it doesn't meet both definitions. Let's look at the next one. In the left column, between up and down, down is better. In the right column, between up and down, down is better. So this is a dominant strategy. And then for player 2, in the up row, right is better than left. And in the down row, right is also better than left. Right, the 20 is bigger than the 2. So both players have a dominant strategy, yes. This is a dominant strategy. Do the dominant strategies lead to a worse outcome? Yes, because player 1 would like this one better, 50 is bigger than 40. And player 2 would also like this one better because 70 is bigger than 20. So the dominant strategies lead to both lower payoffs for both than the other strategies. So this one is a prisoner's dilemma. And you can see I've changed things, right? It doesn't matter if they have the same payoffs. It doesn't matter if it's, the upper left cell. What matters is these two factors. Moving to the next one, let's see. In the left column, up beats down. In the right column, same, so this is dominant. Now here, in the top row, left is better than right because 10 is bigger than 5. In the bottom row, right is better because 50 is bigger than 10. So there's no dominant strategy here for player 2. Player 1 has a dominant strategy, player 2 does not, so it's not a prisoner's dilemma. We don't need to go any further. If the first condition is not met, then the second condition doesn't make any sense. It's not met either. So this one's not a prisoner's dilemma. You can see we have one Nash equilibrium there, which is up and left. But, it may be an interesting game. I mean, for the prisoner's dilemma is just one specific game with a certain pattern of payoffs. We can use this simple two by two table, the 2-player, 2-action simultaneous game, and get a lot of interesting games. I mean, there's other ones that have special names. We're just focusing on the prisoner's dilemma, and we went through that coordination game just to learn, you know, just to get an introduction to it. Looking at this final one, let's see. Down is the best response to left, and the best response to right. So this is dominant. And then here, right is the best response to up, because 12 is bigger than 7. And left is the best response to down. Okay, left is better than right in the down. So here again, we don't have dominant strategies for both. So it's not a prisoner's dilemma. I mean, we can see that, you know, if you compare this payoff to this one, you know, the player 1 is getting 10 either way, and player 2 is getting 12 instead of 0. You know, this is a higher payoff for one of them and the same payoff for the other. You know, that's kind of an interesting situation for the players to be in, but it's not a prisoner's dilemma. It does not meet our definition, which is for both of these things to be true. So hopefully that helped give you a little practice with games and just really hammered in the idea that a prisoner's dilemma is a game where we have these two conditions, and if we don't have those two conditions, we don't have a prisoner's dilemma. Thanks.